Hello friends, let's have a look about the molecular weight distribution and addition, that is the chain reaction polymerization under the edges of chemical reaction engineering in polymeric systems. So in the previous section we have covered the polymerization, step versus chain reactions, step growth polymerization. We started the concept of step growth polymerization. Then we discussed about the various properties of the step growth polymerization, and we started the kinetics of the step growth polymerization. In this particular segment, we are going to discuss with the self-catalyzed step growth polymerization and step growth with respect to the gel point and molecular weight distribution, how we can control the molecular weight. We will have a quantitative aspects of molecular weight distribution. All these things we will discuss in this particular chapter. Let's start with the self-catalyzed step growth polymerization. Now, you have to be sync with the previous lecture because some of the equations we have discussed in the previous lecture. Now, in the absence of, you can say, the externally added strong acid, the diacid monomer, they act as own catalyst for the esterification reaction. Now, for this case, this HA is replaced by COH, and this equation 6, which you recall in the previous segment we discussed, that can be rewritten as minus D concentration of the COH over dt is equal to minus K COH to the power 2 OH. This can be represented as equation number 12. Now here the K and K3, this has been combined in the experimentally determined rate constant K. So this equation shows the important characteristics of the self-catalyzed polymerization, and the reaction is third order overall with a second order dependence on the carboxyl concentration. Now here, for most polymerization, the concentration of two functional groups, they are very nearly stoichiometric, and this particular equation can be written as minus D concentration of M over dt, that is equal to K M to the power 3. This is, let us say, that equation number 13a, or sometimes it can be referred as minus D M to the power 3, that is equal to K dt, that is equation 13b. So where this M is the concentration of hydroxyl group or carboxyl group, and if we integrate this equation, then it becomes 2kT is equal to 1 over M, and that is equal to, initially if the concentration of M is M naught, then this is the equation number 14. Now this in this equation number 14, we have already depicted that at this M naught concentration is at time t is equal to 0, that is at the start. Now it is convenient at this particular juncture to write this particular equation in terms of extent or a fraction of a reaction P, which is defined as a fraction of hydroxyl or carboxyl function group that has reacted at time t. Now P is also referred to as the extent of or fraction of conversion. So the value P is calculated from the determination of the amount of unreacted carboxyl group. Now here the concentration M at time t with either hydroxyl or carboxyl group is given by M is equal to M naught minus M naught P, and that is M naught 1 minus P, sometimes referred as equation 15. Now if we combine the equation 14 and 15 if we combined, then we get 1 over 1 minus P to the power 2 into 2 M naught to the power 2 KT, and this is equation number 16. Now this indicates that a plot, if we plot versus of 1 over 1 minus P to the power 2 versus t, it should be linear in nature. Now at a first glance the plot does not appear to exactly follow the relationship. The experimental point deviates from the third order plot in the initial region below 80% conversion, and in the later stage say above 93% conversion. Now this is the plot. This deviation led various workers to suggest the alternate kinetic expression based on either one or half order dependencies on the reactions rate and the carboxyl concentration, or two and a half order dependencies. Now here you see that the rate equation can be given as minus d COOH over dt, that is equal to K COOH OH. This is equation 17a, and minus d COOH over dt, that is K COOH 3. This is equation number 17, can be referred as equation number 17b. Now the experimental rate data fits this particular equation which we discussed earlier, that is 17a. Well, only in the region between 50 and 86% conversion, with an excessively poor fit above 86% conversion. On the other hand, if we talk about the plot according to this 17b equation, reasonably well up to above say 80% conversion, but deviates badly above that particular point. So neither of the two alternate kinetic plots for based on equation 17a or 17b comes close to being as useful as the third order plot. Now the third order plot fits the experimental data much better than either of the other at the higher conversion. The fit of the data to the third order plot is reasonably good over much greater range of higher conversion region. Now the region of higher conversion is of prime importance, since high molecular weight polymer is obtained only at high conversion. So the practical viewpoint, the low conversion region of the kinetic plot is of little significant. Now, when we talk about the gel point, especially in case of polyfunctional condensation polymerization, the functionality higher than 2 introduce the possibility of branching or cross-linking. Now, in the latter case, it is ultimately possible to attain the molecular weight that approaches infinity. Now, such materials they termed as gel, with the remainder of the reaction mixes with the salts, the sol which is soluble, that can be separated from the insoluble gel. So this occurs because the viscous thermoplastic mass is transformed into the most elastic solid with a very high viscosity. Now, the critical point at which the amount of gel begins to increase rapidly is called the gel point. In order to determine that this particular point, we begin with the specifying the branching coefficient, which is the probability that functional group is connected to an other branch unit. For reaction system, the bifunctional group like AA and BB, they are present along with the polyfunctional units of the polymer. That can be represented by this particular equation 18. You see, you can have a look of this particular equation 18. Now, for this particular equation, the gel formation criteria, that is the least one of the F-1 units, is connected to the another branch unit. Such case has a probability of 1 over F-1. Therefore, the critical A value, or sometimes referred as alpha C, is represented as alpha C is equal to 1 over F-1. This is equation 19. Now, if we relate alpha to the extent of reaction, we can find the relationship of alpha in a more precise manner, which is represented in this equation number 20. So, based on this particular equation number 20, the R is equal to NA over NB, and P is the ratio of A units on branches compared to all A units. So, some of the special cases we have already enlisted some of the special cases or we have represented several conditions like R is equal to 1 and PA is equal to PB. Then what will be the nature of alpha? So we have represented for the ease of convenience that you can roll out the different equations based on these conditions. Now let us talk about the molecular weight control in linear step growth polymerization. So in the polymer synthesis, one is ideally interested in acquiring a particular molecular weight product or a molecular weight distribution product. The characteristics of the polymer, they are highly dependent on the molecular weight. So the molecular weight that are greater or less than the ideal weight, they are equally unwanted. Now, there are many influencing factors like reaction temperature, monomer concentration, closed or open system catalyzed. All these things are the influencing factor in the system. Now, there are various methods which are used for the molecular weight control in linear polymerization. One method is that by quenching the reaction by cooling at the required time and the desired molecular weight, this can be achieved. Another, the disadvantage of this particular method is that the polymer achieved, whatever the polymer which is we are getting, this is highly unstable in nature, and resulting heating this heating contributes to variation in molecular weight, since the functional group or end groups at the end of the polymer molecule can further react. Another way is by increasing the one reactant over other. The polymerization then continues to a stage at which one reactant is fully used up and all the ends of the chain have the same functional group. So, the group which is in surplus. Let us take an example. The polymerization of an excess diamine with the diacid produces polyamide with an amine end group in the unavailability of diacid for the continuous polymerization. So, the reaction can be represented as H2N R NH2 plus HOOC R COH, which is H NH R NH2. Another example, that polymerization of excess diacid with the diamine produces the same result, the polyamide with carboxylic end group in the availability of diamine for further polymerization. This can be represented as like HOOC R COOH plus H2N R NH2 HOCOR NH COOH. Now, another method is by addition of a monofunctional monomer. The monofunctional monomer, also referred as the chain stopper, governs and restricts the bifunctional monomer polymerization. So, the developing polymer produces the chain ends and that are lacking in the functional group and thus unable to react further. Let us take the example. In polyamide synthesis, the use of benzoic acid creates a polyamide Xi, which phenyl end group that are not reactive to polymerization. So, this reaction is represented as H2N R NH2 plus 5 COOH. This can be 5 CONH R NHCO R dash NHR NHOCO5. Now, the quantitative aspect, if we talk about the molecular weight control, and to better regulate the polymer's molecular weight, the stoichiometric ratio of bifunctional monomer or monofunctional monomers must be precisely balanced. If the non-stoichiometry is too high, the molecular weight of the polymer would be too small, and this is essential in understanding every reactive contaminant's quantitative effect that maybe initially exhibits in the reaction medium or is produced by involuntary side reactions. Let us take this quantitative aspect. Now let us consider the different reactant system used in the step polymerization, that is type 1 we discussed earlier. Now the polymerization of a bifunctional monomer AA and BB group is in excess. So the number of functional group A and B are given, the respectively is like say Na and Nb. The number of AA and BB molecules is twice equal to Na and Nb. So the stoichiometric equation can be given as R is equal to Na over Nb, which is less than equal to 1. Now the total amount of a monomer molecule is determined by Na plus Nb over 2, or Na 1 plus 1 upon R over 2. Now the we can say the equation number 2. Now the fraction of unreacted functional group is usually given by 1 minus P and 1 minus Rp. So the total number of unreacted functional group can be represented as Na into 1 minus P and Nb into 1 minus Rp. So the total amount of polymer molecules, they are determined by Na into 1 minus P plus Nb into 1 minus Rp over 2. Let us say this is equation number 3. So the total number of average degree of polymerization dP, and which is represented as xn to the xn bar, is given by the total number of molecule initially present over total number of polymer molecules. So we can represent like average degree of polymerization this is given by bar xn is equal to Na into 1 plus 1 over R over 2, Na into 1 minus P plus Nb into 1 minus Rp over 2. This is, let us say this is equation 4. So when R is equal to 1, then bar xn is equal to 1 over 1 minus P, and when P is equal to 1, then bar xn is equal to 1 plus R over 1 minus R. Let us take an example. Now using this previous equation, find the average degree of polymerization when the conversion is 100% and uses 0.98 moles of AA and 1.0100 moles of BB. So it's quite simple, like we derived this formula, R is equal to Na over Nb. Now here this is given as 0.98, this is for Na, so 0.98 into 2 over 1.01 into 2, and this comes out to be 0.97. So bar xn is equal to 1 plus R plus over 1 minus R, which is 1.97 over 0.03, which is 66. This is our answer. So this is, I mean, you can say the typical example that how we can utilize this thing. Now another thing that which I like to reflect, and that is R is equal to Na over Nb plus 2 dash Nb 1 over 1 plus 2 into 0.01. This is comes out to be 0.99, and bar xn is equal to 1 plus R over 1 minus R, 1.99 into 0.01, that is 199. This is our answer. Now let us talk about the quantitative aspect, that is type 2, the monitoring of the degree of polymerization by adding a small amount of monofunctional reactant to the polymerization of an equimolar mixture AA and BB. So this type of similar equation, type 1, the mole of A group, that is given by Na over 2, and the mole of B group, that is Nb over 2. The moles of monofunctional B is given by Nb. So the stoichiometric ratio of two functional group can be given like R is equal to Na over Nb plus 2Nb. Now here we need to calculate the average degree of polymerization with the number of moles of A and B are given, and each of the number of the moles of monofunctional group Rb is 0.01 when 100% conversion occurs. So I am leaving this particular example, this particular question for your as a tutorial form. Now the polymerization is a combination of polymer molecule of varying molecular weight. Chains with a wide distribution of chain length, they are found in a standard synthetic polymer sample. The distribution is rarely symmetric and involves several high molecular weight molecules. So particularly polymerization parameters, they are influence the specific width of the distribution of molecular weight. For instance, the polymerization of a certain olefins, this can lead to a substantial molecular weight distribution. P.J. Flory, that he derived the molecular weight distribution through a statistical approach focused on equal reactivity of the functional groups. This particular derivation is consistently, like if we derive the size distribution derivation, this is consistently applied to the step polymerization of A, B and AA and BB. This is associated with the possibility of having a molecule that has interacted with the X minus 1A group and unreacted with 1A group. The extent of a reaction P is referred to as the probability that an A group has reacted at time t, and the possibility that X minus 1A group have reacted is P to the power X minus 1, where X is the structural unit. Now the possibility of an A group being unreacted is 1 minus P. So this can be represented as Nx is equal to P to the power X minus 1, 1 minus P, and Nx, this is associated with the mole or a number fraction of X mers in the polymeric mixture. So Nx is equal to Np X minus 1 into 1 minus P. Now this N is associated with the number of polymer molecules. So the overall amount of structural unit initially present is N naught. So N is equal to N naught into 1 minus P. Therefore Nx is equal to N naught into 1 minus P to the power 2 into P to the power X minus 1. This can be represented as equation number 5. The weight fraction Wx of X mers, that is X structural unit, can be given as Wx is equal to X into 1 minus P to the power 2 P to the power X minus 1. This is equation number 6. Now the molecular weight of a number and weight average is given by bar xn is equal to summation x nx and bar xw is summation x wx. So if we put the value of nx and wx from this the previous equation, then the whole equation can become bar xn is equal to summation x n minus 1 into 1 minus P. That can become the equation number 7, and bar xw is equal to summation x to the power 2 P to the power x minus 1 into 1 minus P square. That is equation number 8. Now for several, now if we evaluate the equation 7 and 8, this can be x bar xn is equal to 1 upon 1 minus P and bar xw is equal to 1 plus P plus 1 minus P. The breadth of the molecular weight distribution, which is also referred as a polydispersity index or PDI, this can be given as bar xw over bar xn equal to 1 plus P. Now for several P values of two distribution functions which are shown in these figures, these shows the distribution curve of number and weight fraction of linear polymerized polymers. Now in these plots, the line 1, 2, 3, these are the P is equal to 0.96, 0.9875 and 0.9950. You can easily calculate. Now from this particular figure, we can see that as P is increasing, the number of monomer molecule, they are decreasing. Now, the ratio of the low molecular weight species is relatively small on the weight basis and decreases with increasing P. So, the breadth of molecular weight distribution, the total number and weight degree of polymerization bar xn and bar xw, this can be obtained from the function of a number and weight distribution accordingly. Now, if you see that the initial and a total number of molecule is n naught and n. This is the initial and n is after time t. Then n naught f average is the number of the initial function. Therefore, the fractional conversion is given by p is equal to 2 n naught minus n over n naught into f average, and that is given by 2 1 minus n over n naught, or dp naught is equal to n naught n, which is 2 over 2 minus p f average. Now, when f average is equal to 2, where there is a AB monomer, then dp n is equal to 1 minus p. This is our equation number 10. Now, for sake of an example, this can be given like this: Rm plus again monomer. So, by this way the chain grows repeatedly. Now, this is the chain, again it can act as a proper functional group. So, in bifunctional group, the increased reactivity of one functional group to the other group contributes to overall increase in polydispersity index. If there is a greater than the double rise in the reactivity, the PDI reaches 2 at maximum conversion. When there is a decrease in the reactivity of one functional group to the reaction to the other group, the polydispersity index increases, but PDI at maximum conversion 2. So, dear friends, in this particular aspect, we discussed the PDI, we discussed various reaction kinetics, rate, etc. For your convenience, we have enlisted various references. Exhaustive list of references are here, and you can go through if you need the further reading. Thank you very much.